Okay guys, welcome to this week's video. Now that we've looked at all of the properties of waves, we're going to look at one specific kind of wave, and that is sound. So this chapter 4 is the nature of sound. Now, in this chapter we're going to have 4 different objectives for the week, and this week I thought we were going to do it a little differently, and we're going to be looking at each objective separately. So that means that we will split the objectives up and different groups will take different objectives. So here in the video, we'll look at the objectives one at a time. The first objective says, describe how vibrations cause sound by changing a medium. So here in section 1, we will be looking at what sound is and how that relates to the objective. Now, sound and vibrations. This is the important part of the objective. So as different as they are, all sounds have some things in common. One characteristic is the vibration. A vibration is a complete back and forth motion of an object. So that should sound very similar to what we learned about waves. We saw the waves are moving back and forth or up and down. So the concept of a vibration in a wave is very similar. Now, here we will see sound from a speaker. Now, as the sound wave comes out, remember, sound is a longitudinal wave. So these dots represent particles of the air that the sound wave is traveling through. Here is a compression in the air. So you can see down here, it is compressed. It's almost as though where the air was evenly spread out, the air got compressed into here, leaving a less compressed area behind it. That less compressed area is called the rarefaction. So these are both terms that we should know from longitudinal waves in the last chapter, but as you can see, a sound wave creates this intermittent compression, rarefaction, compression, rarefaction. This is the vibration, the back and forth movement of the air that is created by the sound wave. So as you can see in this image from the book, the longitudinal wave that is being produced by the speaker travels across the room with areas of compression and rarefaction. Now remember, each wave moves out radially from the center. So this wave will spread out, and when it passes by your ear, or this kid's ear, or her ear, it registers as a sound. However, it isn't all sound. The compression is what registers, and the rarefaction is the gap between each sound. So our ears are very well tuned to hear the entire sound, but we're actually hearing an intermittent vibration of compression, rarefaction, compression, rarefaction, compression, rarefaction. And that is what our ears are capable of turning into the sounds that we hear. So, another characteristic of sound is that all sound waves require a medium, the plural of which is media. Now the medium, as we learned also in the last chapter, is what a wave travels through. So, mechanical waves need a medium. The electromagnetic waves we looked at do not. But sound, being a mechanical wave, needs a medium. So this experiment right here is using this vacuum tube to see if you can hear sound in a vacuum. So this tube pumps the air out, and the experiment is to see if you can hear the alarm clock ring in a vacuum. You would find that you cannot. This is why also there is no sound in space. So all of the space battle movies where you hear big explosions, you wouldn't hear an explosion. You wouldn't hear anything because the sound wave has no medium on which to travel. So next we will be looking at this. Objective number 2. Explain how the human ear works and create methods for protecting it. Here we have a nice image of the ear. Now you may think that you just have an ear, but there are actually different parts of the ear. We have the outer ear, which is the part that you can see in the mirror or on other people, which acts as a funnel for sound waves. So this curve that we all have on our ear actually works so that all sound waves entering this will be redirected down into our ear. If you did not have your ear and it were cut off, you could still hear because sound would still enter your ear canal, but you would not hear as well because the ear is helping you to hear sound. So the middle ear is made up of these parts. We have 3 bones: the hammer, anvil, and stirrup. So we have the hammer, anvil, and stirrup. These are bones. They act as levers to increase the size of the vibration. So the lever is a mechanical feature that can be used to conserve energy. So they actually kind of bounce back and forth to what would be amplify the wave that comes in, to make it more noticeable. And then we have the inner ear. Sorry, I have to move down a little bit again. The inner ear, where the vibrations created by sound are changed into electrical signals for the brain. So these bones bounce off the drum into the inner ear, where that sound is then converted into an electrical signal that can be sent to the brain so your brain can interpret it. So sound waves vibrate the eardrum. The vibrations of the eardrum make the hammer vibrate, which makes the anvil vibrate, which makes the stirrup vibrate. The stirrup vibrates the oval window, entrance to the inner ear. The vibrations of the oval window create the liquid inside the cochlea, create waves inside the cochlea. Movement of the liquid causes tiny hair cells inside the cochlea to bend. The bending of the hair cells stimulates nerves, which sends electrical signals to the brain. So there is a liquid in your ear that has little hairs growing in it, and as the waves from the incoming sound energy affect that liquid, the hairs move in the liquid, which make nerve endings move, which sends a signal to your brain. That is how it works. Now, hearing loss and deafness are very real. When we are young, our ears work very well, but the more use that these very small parts of your ear get, the more sound they hear, the more vibrations they endure, the more likely your chance of hearing loss or permanent hearing loss and deafness. So, can you think of any ways of preventing hearing loss? I know for me, the best way would just be to not be around loud sounds for very long. And there are actually many of worker safety laws that require people to have proper ear protection around certain types of sounds. So maybe you can come up with some ideas on your own. Okay, moving on. We will look at objective number 3, which is compare pitch and frequency, and also compare amplitude and loudness. So, the first part of this objective is pitch. I think we've all heard of pitch. There is high pitch and low pitch. So high pitch is the screeching kind of sound, and low pitch is the more bass kind of sound. I guess bass and treble would also be good ways to look at this. We measure them in hertz. So, here we can see the differences between high pitch and low pitch. High pitch is when the compressions or the waves are closer together. They are not quite as dense, but they are much closer together. This is a high pitch. So your ear registers the high pitch by the amount of waves that cross in a certain amount of time, which is frequency. So frequency equals pitch. Next time you hear music and there is a high pitch sound, you can think more waves, faster. Low frequency equals low pitch. As you can see here, the rarefaction and the compression are both larger, and it also means that the frequency is lower because less waves have passed in the same amount of time. Remember, think of this as time. 2 waves have passed in the same amount of time as 4 waves here. So the frequency here is double that of here. The pitch will also be double. Okay? And the second part of this objective looks at loudness. Loudness is just a measure of how well a sound can be heard. So, if we increase the energy, it makes sense that the sound will be louder. It's pretty reasonable to assume you strike a drum harder, that's more energy going into it, so the sound is louder. Now remember, when energy increases, amplitude increases. That was from the last chapter. So, the amplitude of the wave determines the loudness of the wave. A higher amplitude wave will sound louder than a low amplitude wave. This is just another one of the direct correlations between the properties of waves. So, when you turn up this volume, you are turning up the amplitude of the sound waves.
Oh.
So what are you supposed to be?
Me? I'll give you a hint. Meow.
Choo-choo train?
Close. Meow.
If you guessed explain the Doppler effect as objective number 4, then you were correct. The Doppler effect is a very interesting phenomenon that combines the properties that we have been learning about waves and sound waves. As we saw before, sound waves come out as compressions and rarefactions from a source. Now, if a speaker is not moving, then the waves will come out in a very uniform fashion. The frequency, or the pitch, which is determined by the distance between each compression, will be the same in all directions with the stationary speaker. However, if that noise is coming from a moving source, such as a car, or a train, or even an airplane, this movement will actually cause the forward-facing waves, or that is the waves that are going in the same direction as the movement of the source, to become closer together. That is to say, they will have a higher frequency and also a higher pitch, whereas the waves that are not going in the same direction or traveling away from the moving source in the opposite direction will be more spread out, have a lower frequency and a lower pitch. So, this is why that if something that is making noise and traveling quickly moves by you, it will sound different as it approaches and then leaves. The approaching sound will be different from the leaving sound. That is the Doppler effect, and it has very many interesting applications in the real world for understanding the movements of things, using radar, weather. It was even part of what Einstein had to consider in his formulation of relativity. Could you explain the Doppler effect to the party guest? Not quite sure what it is.